Okay, good morning, everybody. As said, I'm come from Israel, working with the Israel Institute for Advanced Research. We are trying to, in vain in these moments, to install a new way of thinking and a place you can fail with new ideas. Anyway, thanks. I want to thank Jerry and the organization for inviting me and having this opportunity to express my ideas alongside with other people here. You know, I feel myself working in the verge of accepted scientific thinking, but in the realm of this conference, I feel like I'm a very established conservative scientist. So I'm just breaking the dogma of chemistry, big deal. People are talking about fantastic ideas, and it has to be done. So thanks people that, Jerry and the others that gave us this opportunity. So I'm going to talk about this rather provocative name of the talk, and it has to do with water chiral. Actually, it's deviation from identity of macroscopic properties of an enantiomer, probably via water chiral preference. So just to show some symmetries, is that the picture of right and left polypeptides, and the same symmetry is shown in this is a kudu, an animal from Africa, and the drawing was done by Darwin itself on his way to Galapagos. So you see the symmetry, left and right symmetry, like the peptides in this animal. I will say some things about the historical background of all the field, some introduction. I will do some experimental description. That's the base, that's the center of my talk, the experimental evidence, where we talk about plausible explanations we have, but they are not the core of the thing. I mean, if the other ones will come with better explanation, that's fine. And the work is done was pioneered by Professor Meir Shinitsky, and he's still working on it, and it's done in collaboration with Professor Dimmer and Professor Ben Yaakov, among others. So, the core dogma of chemistry is that chiral isomers are perfect mirror images, identical in their macroscopic properties. And our work, I believe, provides the proof of macroscopic differences between chiral isomers, in contrary to the mentioned dogma, probably in water solutions okay. So some historical background. Now, the field is called chirality, it's handedness. It has to do with symmetry, a basic symmetry of materials and the universe and the molecules and everything so on. And chirality is the word for, chiral is the word in Greek for hands. Now, it's very easy to see it. If you look at your hands, you will see that they have this symmetry of reflection. I mean, if there is an imaginary mirror between them, then left hand looks like it's a mirror image as a left hand, and you cannot superimpose them. That's chirality, and it's going down to molecules and organic materials and everything else. Now, ancient people, the notion that the physical world is handedness comes from ancestral times. It comes out from the anthropic principle that the microcosmos, epitomize the universe. And since we have chiral similarities between us, then the cosmos must be so. Louis Pasteur said it in French. I was not going to do that. It will insult the French language. So, why it doesn't move? Okay. So, the universe, as strange as it sounds, is not symmetric to left and right. in the very basic way it's built. And from atoms to humans, nature is asymmetric with respect to chirality, or left and right handedness, as you said. Okay, so most objects are not identical with their mirror image. Processes, such as chemical reaction, may exhibit chirality. And you begin with left-handed materials and you end with left-handed materials, and vice versa. Now, certain atomic and nuclear interaction. So with no a priori reason, the real world usually displays chirality. Examples, right-hand people. So the crucial point is that molecules can be chiral also. Now you see the very simple example, the center of inversion here, and if you have around in certain point in your molecule, you have a carbon with 4 different substances related to it, then it will show chirality. You see if you pass here the mirror, image the mirror, you see that this molecule is the mirror image of the other one, like as hands that show. So, as I say, the basic, let's say, emphasis again, the basic dogma of chemistry is that the macroscopic properties of these enantiomers or chiral materials are completely identical, except for the trivial fact that they react differently with polarized light, left and right. So, if you come to the biology, we can see that all the 20 amino acids that constituent the proteins in all the living biosphere are made of the right-handed, the L amino acids. Sugars are D by definition. So the reasons for this preference of life, that's a big mystery. Why life, if the dogma is that the L and right and left are identical, so why life preferred L enantiomers? Part of the explanation that is by sheer luck, I mean. But it seems you have to look at it to the subnuclear scale, so let's move there. All non-nuclear particles interact through 4 types of forces: gravity, electromagnetic force, strong nuclear force that holds atomic force together, and the weak nuclear force that is responsible of radioactive decay, beta rays, electrons coming out from the nucleus. Yeah. So, till 1957, the assumption was that the 4 forces are parity conserving, meaning they react the same with the process and its mirror image. They are impervious to chirality. It was found that the parity, the weak force is responsible for radioactivity, is not parity conserving, sorry. It's the results, the showing of chiral asymmetries, left-handed electrons far outnumbered right-handed electrons, and other elementary particle, only one of the 2 possible chiral exists, left-handed neutrino and right-handed antineutrino. So that's an expression of the basic chirality of the universe as it is in the nuclear realm. Now, we don't know what's the reasons at fundamental level. It was believed that parity is confined to nuclear reactions. And interactions of atom and light seem to conserve parity, but the new electroweak force found by Weinberg, Salam, and Glashow showed that turned out to be non-conserving parity. Then, because the electroweak force distinguished between left and right atoms and molecules must be chiral in the nuclear sense of it, in the basic sense of it. Now, In order to see on macroscopic realms, this chiralis asymmetry well accepted in the very basics level, we need some way that their linkage and grow up. So it may be by the electroweak force. Now the electroweak force causes a chiral molecule to exist in a lower ion level than its enantiomer. This tiny effect was not observed, but is accepted as a theoretical calculation. The effect is very, very tiny, about 10 to the minus 17 electron volt, or 1 million molecules in a more racemic mixture. It's very, very slow level of difference, and the accepted dogma says that this small difference cannot be transferred to the macroscopic realm. Now, in principle, it can be done if you apply an external autocatalytic process, then even a very small difference might prevail. So our work is in the realm of that, of the linkage, of the transference, and possibly this linkage is a chiral nature of water to be demonstrated. So let's go a little bit to what I wanted to do before. I'll try to show 3 different results we have and some explanations, experimental approaches. So let's begin with peptide transitions to alpha helix. That was published. Polyglutamic acid and polylysine are water-soluble polypeptides will undergo structural changes from random coil to alpha helical structure. They have a distinctive circular dichroism. Circular dichroism is the way to measure circular to see the circular dichroism, that's secondary spectra of molecules and so on. This is a glutamic acid, and it's a polyglutamic acid is a polymer of that. And so circular dichroism measures differences in the absorption of left-handed polarized light versus right-handed polarized light. And then you can get your chirality and your secondary structure of your materials. That's the way to do it. That's the way spectra looks. I mean, you see alpha helix and beta sheet and random coils. They're all structures of proteins and peptides. The ellipticity or the measure of chirality and wavelength. That's the normal things. Now, here we see the examples of our work in poly-D and poly-L glutamic acid. You see that as it should be, in the helix realm, they are identical. But in the random coil realm, it's a very much less structured region. You can see differences between the poly-L and poly-D in water, and in water and in D2O. I will go to that. And you can see that they're almost identical that the poly-D is identical in water and in D2O. So that's the first show of differences, macroscopic difference in water of chiral materials that it should not be. It should look like this in the identical spectrum. We have done, now, as we see in the farmers, D2O, going to D2O, markedly affected the CD spectra of poly-L, but none effect almost on the poly-D. And that's one of the things we will use to our explanations. That may be from the random coil, small differences in energy show themselves. So we move to do ITC, isothermal titration calorimetry. And there's very, very exact method to measure enthalpy. That's the setup you compare between the reference cell and the sample cell. You compensate when the reaction is done on the sample cell. And you can see 3 different regions. I don't go into elaborate on that, I don't have the time. But you can see here the differences in enthalpy between poly L and poly D, and that's in water. But when you move this to D2O, heavy water, that's the most closest liquid you can think about water, and we use it to compare it. We see that this difference is abolished. So the result indicates you have to ionize the change to get this transition, and the degree of ionization can give you an indication to the tendency to transform from random coil to adopt a helix structure. So our results indicate a stronger tendency of poly-D-glutamic acid to adopt this structure. Completely against the dogma, as said. That's a difference in energy. Now, it's very important that the abolishment of the difference between the enantiomers, the same materials, the same solutions in D2O, this overrules the possibility of undetectable flow in their synthesis. That's the answer I always get from people saying, well, they were not synthesized the same, so you get differences. Now, you cannot explain that if in D2O, you get the same result, identical. So it cannot be if it were synthesized not the same, the difference will show in water and in D2O as well. We even get to the extreme to synthesize it with 1% glutamic acid impurity to show the strongness of the results, and that was corroborated by the other group in Greece that gave us a lot of strength to go on with our studies. Now I want to say, so the interpretation is that poly-D-glue has a higher helix stability than poly-L-glue, glutamic acid, of course. So in a way, you want to say that poly-D glutamic acid and lysine, of course, we have done the same with other materials, is an apparently more hydrophobic nature. So, main thing, now the difference is abolished in the D2O, besides being important to the impurity problem, gave us some clue about what might be the reason. As we said, we need some amplification of the parity violation energy difference I talked earlier, this small difference, 10 to the minus 17 electron volt. But the first of our amplification methods is the autocatalysis of helix formation. I mean, when the first part of the helix is formed, the others are easier. So the autocatalytic system, the more important seems to be the water chiral preference. As shown, water is more akin to react with L than with D. So one of the explanations we give is that bulk water is a mixture of ortho water and para water in the sense of the nucleus of the hydrogen. The spin is up or down. So the up and down gives you a tiny magnetic moment. That's known. Now, so ortho water, that's the majority in water, is a magnetic dipole. It has a slight preference to react with L enantiomers that due to parity violation energy difference induce also a very tiny magnetic dipole in L enantiomers than D enantiomers. Now, if that was the case, then the selective effect of the isomers, spin isomers of H2O will be greatly diminished in D2O. Now, D2O, that doesn't have spin isomers, and then it doesn't have magnetic dipole. It has to do with nuclear, only even per number of constituents of the nucleus have a spin, and then deuterium doesn't have spin. And that's what we found. Indeed, that's what we found. That gives us some assurance of this explanation. The main effect is on L. That is the one that bears a magnetic, tiny magnetic dipole. D is indifferent to the magnetic dipole of water. So I want to move quickly to two other experiments we've done to show this point. Now it's mirror symmetry breaking, self-assembly of L and steroyl enantiomers. As said before, we use the circular dichroism spectra for record micellar aggregates or micelles of N-steroyl in DDW, in double distilled water, or D2O. These materials forms micelles in time, and we found that the micelle formation kinetics in final form were different for L and D in water. Now this is stearoyl serine. You see the serine and the hydrophobic tail. So if you neutralize the side chains of the hydrophobic tail, these tails tend to get together from hydrophobic reasons, interactions, and then you get what I call a quasi-peptide. I mean, the serine began to behave like a quasi-peptide, only with a hydrogen bond instead of the chemical bond that should be there. Now, this micelle is so delicate that it can react to very tiny differences in things. So it's a very good instrument to search these kinds of interactions. So as said, these two, as they show differences in water, but they show similar spectra in D2O. So here is the show. As you see, this, the red one, is L. And this is direction of time. It's one after the others, as you see here. And this is the spectra of D, stearoyl serine. Now you see a clear and cut difference. Now, one very interesting point has to do with maybe two-water state or so on, is that, as you see, the D serine began to form in a certain way, and suddenly it shifts to other micelle formation. Now, for me, this might be a clue of the two states of water. I mean, in a way, till the micelle gets to a certain growth, then it meets the chirality of water. That chirality that has to do with the two states. I might try to get a number of this size, and then I may get some estimation. What's the size of the two-state water? That may be very important. Then you can begin to discern between different models that are around. I personally believe more in the Philippa Wiggins two states of water, but there may be other explanations of that. And that is in top of the auto-water explanation I gave before. Now, if there are still people of Grander here, just to mention that I use these molecules to research their water because of the delicate state it has and the comparisons between D and L, so I can get some information about the water. I mean, using it in the other way around, searching the water. So now that was the differences in L in water. As you can see, when we move to D2O, L becomes very, very similar to D. So again, we have a preferential interaction of water with L, and that is abolished in D2O water. It's a clear and cut thing. Now I have done some other experiment, very interesting. I don't have yet the explanation. We used, let's try to shift or to break the structure of water. One of the ways to do it is, of course, to use alcohol, methanol do it very well. There is a lot of works about the way they miss or coalesce, or there are people that are saying that methanol in water is there are two coalescing liquids with certain safe domains of methanol and water and some penetration between them. So when we look at that, we see this very, very interesting graph. Now, the upper part is L in water plus 10% methanol. The second is D in water, Serine, Stearoyl Serine in water, how it's formed. This is L in water with plus 10% methanol. And this is D Stearoyl Serine in water and plus 10% methanol, and the two spectra are identical. I cannot discern between them. Okay. So let's move to a third result. Now we are talking about L and D-Alanine, optical activity in water and D2O. We are just taking just very well purified alanine, and we're checking how it is dissolved in water. So this is, I just multiplied by -1 the D. So you see here the effect of, again, D and L in D2O, the lower two closed graphs are identical, and you see the differences. Sorry, this is the ones. The upper one is in D2O, and you see the difference between in water of L and D. But it's very interesting that, why it moves back? Okay. It's very interesting to see the influence of the concentration. We see here, we increase in concentration, and we see here that the optical activity is not linear with concentration, but it differs in a certain point, and it's different for L in water and D and L in heavy water. Now, if you look now in L in heavy water and D in heavy water, we see again identical graph. And just to complete the story, we see L in water and D in water, and we see the differences we mentioned up to a certain point. Now, this accidentally or not, as you see, you have different in D, as I said, they are different in double distilled water, identical in D2O. Now, the source of the difference is interesting because, as you see, the optical activity is not linear with concentration. So that means that alanine is wandering around in water in clusters. Now, as known as clusters are formed when you increase concentration, but the optical activity, the effective concentration is less. I mean, molecules are basically hiding one behind the other, so the entering radiation doesn't interact with all of them. So this kind of behavior, a nonlinear dependence of activity is plausible that it's clustering. So that it's a very nice result of itself that alanine is wandering around in water in clusters and not one molecule surrounded by water. So, yeah, Yeah, I know. No. I cannot stop it. Okay. So, complications and conclusions. Okay. One moment. Implications and conclusions. Too much. So the chiral preference of water can be the amplification mechanism we were looking for, and this may explain the life preference to L enantiomers. And obvious implications of water, as I said, and I began with a question mark, I will finish with a affirmation mark. I think water is chiral. Thank you very much.